Welcome to the last part of this video. We have been working on an example of a oil refinery process where we have formulated the QP problems, and in this video we will be solving the mathematical QP problem by using a solver named qpoases, and we will be using Simulink to solve the QP problem for the oil refinery process. Before moving forward with this video, please have a look at the previous video if you have not looked. To refresh the process, let us have a look at this block diagram. It's an oil refinery process and there are 6 variables to optimize. They are denoted by x1, x2 all the way up to x6. We want to optimize these values of x from x1 to x6 such that we maximize the profit obtained from the oil refinery. To do that, we formulated a QP optimization problem for the oil refinery, and we also took into account all of the process constraints present in the process. Finally, we formulated our objective functions and the constraints in a standard form or in a form that is actually supported by our solver. And here is the form that is supported by the qpoases solver. H is the Hessian matrix, which is shown here. C is a vector containing the coefficient of the linear terms in the objective function. This is a general way of expressing both the equality and inequality constraints, and these are the bounds. The values of A, B, XL and XU, including H and C, have been calculated already, and the details are shown in the previous videos. Here are the values that have been listed. So now we have a problem at our hand, and we will be using Simulink to solve this problem. Go to MATLAB and open up Simulink. Choose the blank model, and here we will be making the QP problem for the oil refinery process. The basic plan is that in Simulink we will be using a block for defining our matrices. Let's name this block as QP problem formulation block. And in this block we will define our matrices H, C, A, B, XL and XU, which are needed for the solver. And we will pass out this data after calculating, and then we will be using this qpoases solver to solve the problem, and out from here we will get the optimal values for the x. Okay, now let's try to implement this basic block diagram in Simulink. In Simulink we will make use of the MATLAB function block to write our matrices. So this block will be defined in a MATLAB function block in Simulink. Click on the library browser. The MATLAB function block is available under user-defined functions, and here is the MATLAB function block. Let's use it. Drag and drop to the workspace. Let's double click it to go inside. By default, this will be added, but we can safely remove it. In this function, we don't need any inputs. The system will only give out the 6 outputs necessary for the solver. Thus, in Simulink, we will not have anything in the input field. Now let's make all the matrices and vectors necessary here. First, let's start with the Hessian matrix. We already know the Hessian matrix, so it's simply to type it here. The Hessian matrix is a diagonal matrix, and these are the elements that are on the diagonal. Let's have a look at it from the previous video. So this is the Hessian matrix, and these are the diagonal elements. So to make these matrices, we only need to have these diagonal elements, because all of the remaining elements are 0. In MATLAB or in Simulink, there is a function called diag, and we pass the vector containing the diagonal elements of the matrix. If you type this matrix in the MATLAB command window, you will get the following output. So this matrix looks the same as in here. However, there is one important point to be discussed here. Since we will be using qpoases solver, the qpoases solver does not support matrix, and sadly this is a matrix. The qpoases only supports vector. So we have to rearrange this matrix into vector, and that is just because of the solver that we have been using or that we are going to use. To change this matrix into vector, we will stack the elements of the matrix column wise. To stack the matrix in column wise, in MATLAB we do the following. With this command, the elements of this matrix will be stacked column wise and a vector will be produced. And we'll be using this edge with the qpoases. Okay, so now let's make the C matrix. The C matrix is here and we just need to type it. Similarly, the A matrix, B matrix, XL matrix and XU matrix should be typed as shown here. Similarly, this is an A matrix, and as also described earlier, qpoases does not accept matrices but only vectors. So this matrix should also be changed into vector, and to do that we will stack the elements of this matrix column wise. Finally, we will enter the right hand side of the equality constraints and then the bounds. Now we have typed or made our problem formulations, and we have all the necessary matrices and vectors needed by the solver. Now we have to pass these matrices to the solver. Out from this block, we have to choose appropriate matrices and vectors. The first thing I will pass is the Hessian matrix, and then the C vector, and then comes out the A matrix, and then the bounds, and finally the right hand side of the equality constraint. Let's also give an appropriate name to this function. Save it to an appropriate location, the Simulink model file, and give it an appropriate name. Now we have the QP refinery problem, and out from this block all of the necessary matrices are given as output. Now we need to solve using qpoases. Before we can solve using qpoases, we need to first compile the qpoases C++ codes. To compile it, we have to go to the place where qpoases was installed or was extracted. For this example, we extracted the qpoases in the C drive. We go inside this folder and we will look for the Simulink interface. Here are the C++ source code for the solver. Now we need to modify this C++ file so that it fits exactly the problem that we are going to solve right now. Double click this CPP file. Inside this file, scroll down and go to the settings. Leave it as default of 0.1 second sampling time. We don't need it, but we need to change this one, and this one is the number of unknown variables to optimize, or number of decision variables. For the oil refinery problem, our number of unknown variables to optimize is 6 of them, from x1 to x6, so we replace this by 6. We can increase the maximum iteration from 300 to, let's say, we choose 5000. The type of Hessian can also be changed here. Here we can keep it as Hessian to be semi-definite. A semi-definite Hessian is a Hessian where the diagonal element also has 0 elements. If you look back here, the diagonal element has 0 in many places except these 2 places. So this Hessian matrix is semi-definite. So since we already know the knowledge of this Hessian matrix, we can define it in the C++ source file. We define it as shown here. If you don't know the type of Hessian matrix, then we can define as Hessian type is unknown by using this instead of using this. Now, there are no other more modifications to make to this file. Save it. You can close this file. Go back to your MATLAB folder where you are inside the qpoases Simulink interface folder. Now we need to compile this file. To compile this file, type make and the name of the file. The name of the file is this one. For easiness, we can simply copy it. We have to give the name inside inverted commas, and here we can paste the name which we recently copied. Press enter. After a while, you will receive a message saying that the mix file has been completed successfully. With this message on the MATLAB command window screen, we should know that the source file was successfully compiled. And the compiler that was used was MinGW64 compiler, which is the GNU GCC compiler. Now we have this mix file. We should copy this mix file and go back to the folder where our model is present. We are working with the oil refinery problem, and here in this folder we can paste the copied mix file. Please note that you should not rename the name of this mix file. Back into the Simulink window. To use the mix file, we will use a block called S function. Click onto the library browser. The S function is also located under user-defined function. We can use this for making use of the mix file. Drag and drop it. Double-click this file, and in the parameter field where S function name is stated, you should write the name of the mix file. The name of the mix file can be copied for easiness. You don't need to type the extension MEXW64. This is not necessary. Only the name of the mix file should be here. Click on OK. Now your S function will have the ports that accepts all of these matrices and vectors. The first port is for H, we connect it. The second is for C. The third is for A. For this last one, this solver takes as an input the lower bound of the inequality constraint or the general constraint. It takes B as the last input and also B as the second last input. It takes the lower value for the second last input and the upper value for the last input. But since for our equality constraints these are the same, it's just the same B and B, we will do the same thing in the block as well. So this B goes to both of them. Now we are ready to solve it. From the first output port of this S function, which is the solver, from the first output port of the solver, we get the optimal values. We can plot the optimal values. Let the number of inputs be just 1. Let's give a legend, and these are X optimal. Double click on the scope, go to the settings, click on Open at Simulation Start, click OK. To view the legend, click on View and click on Legend. You can close this graph. Save the file, and now we are ready to run this model in Simulink. Click on Run. And here in this graph we see the optimal values for all of the X variables from 1 to 6. We can close this one, go to settings, and it is not necessary for us to simulate for 10 seconds. This is an example of static optimization, so we could have simply also selected 2 seconds. And in addition, we could have also used fixed time step solver with Runge-Kutta fourth order and with a sampling of or a step size of 0.1 second. Let us rerun it. It gives us the same results as before. The legend says that the best or the optimal values for x1 is given by the yellow line. Similarly, for x6 it's the blue line. If it is difficult for you to know the exact value of these lines, we can look the Simulink figure in a MATLAB figure window. To do that, right click on this figure window and then select Print Display to Figure. And here we have a full-fledged MATLAB figure window where we can use all the functionality that is given by the MATLAB figure window. To know the exact value of these lines, click to the data cursor. Let's check, for example, the yellow line, which is for x1. Click anywhere on the line. And it shows that the optimal values for x1 is 1.5 into 10 to the power 4 barrels per day. And similarly for x6, which is this line, the optimal values is 2000 barrels per day. Thus, in this video, we have used the MATLAB function block in Simulink and the qpoases solver for solving a QP problem for the refinery process.